If we want to figure out how to evaluate monomial traces at Cauchy-Johnson basis elements, it makes sense to study how monomial traces are related to other traces. One of the simplest relations is the relationship between the induced trivial characters and the monomial traces. So recall that the homogeneous symmetric function is basically defined to be a sum of all monomial symmetric functions. So that means that monomial traces, induced trivial characters are the same sum of monomial traces. So with q equals 1 or for general q. So if we know a set H with say the induced trivial character, actually with n it's just a trivial character. So the trivial character evaluated at the Cauchy-Johnson basis equals the number of elements in H. Then it makes sense to think that maybe we can write H as a disjoint union of subsets m lambda with the number of elements in each subset m lambda equal to the monomial trace evaluation. Or if we're summing over, say, all tableau in H, q to some statistic of the tableau, maybe that's equal to a sum of all partitions of n, a sum of overall tableau in the set m lambda, q to that statistic applied to the tableau u. So for example, we have the trivial character eta n evaluated at Cauchy-Johnson basis element equal to, well, this is a sum of monomial traces evaluated there. And we can write this as the number of row semi-strict PFW tableau of shape n, or the Q version, and we don't exactly know a Q version of this statement, but we know a Q version of another statement, and that is the evaluation of the trivial character of the Hecke algebra at the Cauchy-Johnson basis element is a sum over row closed, left row strict tableau, FW tableau of shape n, Q to the number of right inversions in U1 concatenated with U2, etc. Where we, or actually, if this is just a tableau of shape n, then we don't need to concatenate anything because it already is a one-row tableau. So the number of right inversions of U. And actually, it's sort of silly to say row closed because if we have everything in one row, obviously we'll see all indices 1 through n in that one row. So we can leave that out of the definition. So let's do an example. So for example, let's look at the permutation W is 1, 3, 4, 2. With descending star network looking like that, and the poset is 1 less than 2 less than 4, 3 incomparable to 2 and 4. So if we look at row semi-strict PFW tableau, that is, so 8 of 4 counts, I'll just say 8 of 4 of C1342 equals 1 because of 4 tableau that we can draw. So we have 1, 2, 3, 4. These are row semi-strict. 1, 2, 4, 3 is legal. 1, 3, 2, 4 is legal. 1, 3, 4, 2 is not because 4 is greater than 2. 1, 4, 3, 2 is legal. Now it's possible to compute that phi 3, 1 of this Kajdan-Lustig basis element equals 3 and phi 2, 1, 1 equals 1. So we might ask which one of these tableaux corresponds to the phi 2, 1, 1 evaluation, so that the other 3 correspond to the 3, 1 evaluation. So which one corresponds to this, and which 3 correspond to phi 3, 1. And then we can do the sum version. So if we're looking at left row strict FW tableau, these are of arbitrary type. So we'll definitely have 1 to 1 because that's the only place a path starting at source 1 can go. And we could have 2, 2, 3, 3, 4, 4. Or we could have 1, 1, 2, 2, 3 could go to 4, and 4 could go to 3. We could have 2 go to 3 and 3 go to 2. Or we could have 2 go to 3, 3 going to 4, and then 4 going to 2. Alright, now if we compute right inversions, I guess there's none here because the right indices are 1, 2, 3, 4 in that order. Q to the 0th is 1. 1, 2, 4, 3. 3, 4, and 4, 3 intersect, so that's Q to the first. And then 1, 3, 2, 4. 2, 3, and 3, 2. 2, 3, and 3, 2 intersect, so that's another Q. And here we have 3, 4, 2. 2, 3, and 4, 2 intersect. 3, 4, and 4, 2 also intersect. So we have Q squared. So eta 4 of C1342 equals 1 plus 2Q plus Q squared. Now it's possible to compute the monomial trace evaluation. So phi 3(1) of this is equal to 1 plus Q squared, and phi 2(1,1) equals Q. So you can see they add up to this. So we can ask which tableau. Now since we've got Q's in here, we're narrowing things down a little bit. Here, when we ask which one tableau corresponds to phi 2(1,1) evaluating to 1, all four of them look maybe equally likely. But here, we know that that one tableau is going to give us a statistic of Q. So it's either this tableau or that tableau. So which tableau with statistic value Q corresponds to the evaluation of phi 2(1,1). Now these are open questions. I don't have the answer. This is just a suggested strategy for further research in the area. The end.